So right now we can understand one thing is that the sampling frequency should be large so that the loss of information in the process of sampling is less. We have discussed frequency spectrum of the two signals, one x of t and one sampling signal. But what is more important is the frequency spectrum of the sampled signal. So we are going to draw something in this third position, which will be Fourier transform of the sampled signal. Once we can do that, we will be able to derive the criteria that we were talking about. So let's first go through a mathematical analysis and then we'll come back to this particular slide and we will draw the frequency spectrum of the sampled version of the signal. So we are discussing ideal sampling. We have understood through waveforms how signal x of t is converted into its sample version. So basically we have signal x of t, a sampling signal s of t, and we generate a sampled version of the signal. I call it xst. S as a suffix represents sampled version. We had concluded that to generate xst, all you have to do is multiply x of t with s of t. Now this is what we do in time domain. This is time domain operation. Our aim is to draw the frequency spectrum of xst. For that we will have to take Fourier transform. We'll have to find Fourier transform. So if I take Fourier transform on both the sides, then I will get xst. I will call the Fourier transform as xs of f. I will call it xs of f equal to x of t will have the Fourier transform x of f. We already used this notation x of f. S of t, the Fourier transform is s of f. We have also used the notation. In fact, we have shown Fourier transform of both x of t and s of t in the form of waveforms in the previous slide. So this is my Fourier transform x of f of x of t, and s of f which is the Fourier transform s of t, and that also comes out to be a train of impulses. Now the one last thing that will give us this complete valid expression is to understand what happens to multiplication. When you multiply two signals in time domain, we all know that we take convolution in the frequency domain. So this is frequency domain operation. So when you multiply in time domain, we take convolution in the frequency domain. Now let us write down mathematical representation of s of t. It's a sampling signal. It's a train of impulses. Train of impulses can be written as summation del of t minus kts, where k will vary from minus infinity to plus infinity. You can verify this mathematical representation. It's called a train of impulses in time domain. If I put k equal to 0, then I get delta t, which is the impulse at origin. If I put k equal to 1, I get del of t minus ts. It is an impulse shifted by ts towards right. If I put k equal to minus 1, I get del of t plus ts. It's an impulse shifted towards left by ts. And because k is varying from minus infinity to infinity, you have various impulses which are shifted by amounts like ts, 2ts, 3ts on right hand side as well as on the left hand side. So that's my train of impulses. Now if I take Fourier transform of s of t, it comes out to be that Fourier transform s of t is nothing but a train of impulses again. So we have the same train of impulses, but this time it is a function of frequency f, the Fourier transform, and the gap between the two impulses, which was ts in the time domain, is now fs in the frequency domain representation. So that's my train of impulses where k will also again vary from minus infinity to plus infinity. And when you take the Fourier transform, if you remember, we have a constant appearing outside, which is 1 by ts. I can also replace 1 by ts with fs. So if I go back to my original expression in which the sampled signal has the Fourier transform of x of f being convolved with S of f. Now S of f is nothing but, we have just got S of f, it's 1 by Ts summation del of f minus kfs. If we take this ahead, you can see we can keep 1 by Ts outside, it's a constant, and because convolution is a linear operation, I can exchange convolution and summation. Both convolution and summation are linear operation, so I will keep summation outside and I'll send this x of f inside. So x of f is now convolved with the train of impulses, which is del of f minus kfs. The range of k will still remain the same.